Okay, let's talk about solar power. We're going to go on a journey exploring the very heart of how solar cells work, from the fundamental science to some truly futuristic materials that could one day power our entire world. We'll see how this amazing technology has evolved and, where it's headed next.
But first, why does all this matter so much? Well, this chart really puts it into perspective. For hundreds of thousands of years, atmospheric CO2 has gone up and down in a natural cycle. And then, look at that spike on the far right. That's us. That's the Industrial Revolution. And it's exactly why the global search for clean energy is so incredibly urgent.
So that brings us to the big question. The sun just drenches our planet in energy. I mean, there's more solar energy hitting the Earth in a single hour than all of humanity uses in an entire year. The power is there. The real challenge has always been the technology. So how can we get better, and I mean way better, at capturing it? To figure that out, we're going to take a trip through the past, present, and future of solar cells. We'll kick things off with the basic science, how it all works. Then we'll dive into the first and second generations of solar panels, check out what the future might hold, and then, at the end, we'll tie it all together.
All right, let's start at the beginning. We're talking about the fundamental magic that's happening inside every single solar panel out there.
It's called the photovoltaic effect. And really, it's just a fancy way of saying you're turning light, these little packets of energy called photons, directly into electricity. And this whole process, this little bit of magic, happens inside a specially engineered semiconductor device known as a PN junction. That's pretty much the engine of the solar cell. So how does it actually work? Well, think of it in 4 steps. First, a photon from the sun smacks into the semiconductor. Bam! It has enough energy to knock an electron loose, leaving behind a little empty spot, or a hole. Now, that PN junction we mentioned, it acts like a tiny traffic cop. It uses a built-in electric field to push the electron one way and the hole the other way. That separation creates a voltage. And if you connect it to a circuit, you've got electricity. Simple as that. Okay, so that brings us to the technology that really took this process and scaled it up for the entire world, the first generation of solar cells. First-gen cells are all about one thing, silicon. Specifically, something called silicon homojunctions, which just means all the important bits are made of the same basic stuff. These are the absolute workhorses of the solar industry. I mean, they dominate the market for a reason. The tech is mature, it's super reliable, and it's become pretty cost-effective. Whether you're looking at those sleek, all-black monocrystalline panels or the more common blue-flecked polycrystalline ones, this is what you're seeing on rooftops everywhere. But there's a catch. For all its good qualities, silicon has a fundamental physical flaw when it comes to solar power. It has what's called an indirect band gap. And what that really means is that it's just not naturally great at absorbing light, which for a solar cell is kind of the whole point, right? So scientists and engineers knew they could do better.
And that search for something better brings us to the second generation. This was all about overcoming silicon's biggest weakness by, well, doing a lot more with a lot less material.
This is the key difference, right here. With silicon's indirect band gap, getting an electron excited is like a 2-step process that involves both energy and momentum. It's just less likely to happen. But with direct band gap materials, like CIGS, it's just a simple 1-step jump in energy. It's way more efficient. And that efficiency means you can absorb the same amount of sunlight with a layer of material that's literally hundreds of times thinner than a silicon wafer. And because these layers are so incredibly thin, it just opens up this whole new world of possibilities. Second-generation materials aren't cut from big blocks. They're created using these highly advanced techniques to deposit them, atom by atom, onto all sorts of things. Glass, flexible plastic, even steel. And the science behind this stuff is just awesome. You have co-evaporation, where you're essentially vaporizing different metals in a perfect vacuum to create this perfect alloy film. There's sputtering, which uses high-energy ions like a microscopic scalpel, just carving atoms off a target and placing them precisely onto a surface. And then there are even more advanced methods, like LTP'd, which uses a powerful electron beam to create a plasma that builds a perfect film without needing crazy high temperatures. So why does all this high-tech manufacturing matter? Well, imagine a skyscraper where the windows themselves are generating electricity. That's the whole idea behind building integrated photovoltaics, or BIPV. You're not just sticking panels on the roof anymore. The building itself becomes a power generator. This is where thin film technology really starts to get exciting. But, of course, the search for the perfect solar cell didn't stop there. Now let's look at the third and fourth generations, where scientists are pushing the absolute limits of what's even possible.
Okay, just look at this number for a second, 46%. That's the record efficiency for a third-generation solar cell. That means it turns nearly half of all the sunlight that hits it directly into usable electricity. I mean, that's absolutely incredible. So the obvious question is, why isn't this on every roof in the world? Well, here's the trade-off. Crazy complexity and cost. These are called tandem cells because they work by stacking multiple super sophisticated layers on top of each other, where each layer is perfectly tuned to capture a different color of light. It works beautifully, but it makes them ridiculously expensive to produce, so for now you really only see them in super specialized places, like on satellite. And that brings us to the fourth generation, the wild cards. Right, if the third generation was like a Formula One car built for pure, uncompromising performance, the fourth generation is all about changing the rules of the game entirely, focusing on super low cost and really innovative materials. And here you can see the two leading candidates, and it's all about trade-offs. On one side, you've got dye-sensitized cells. They're incredibly easy and cheap to make, but they're just not very efficient. And on the other side, you have perovskites. These are the real rock stars of solar research right now. They offer high efficiency, almost as good as commercial silicon, but for a fraction of the cost. The massive challenge? They break down really fast when they're exposed to air and moisture. Solving that stability problem, that's probably the single biggest quest in solar research today. Whew. Okay, so after that whirlwind tour through the world of solar, let's just take a step back and quickly summarize this whole journey. Here's the whole story in a nutshell. We started with Gen 1 silicon, the reliable, old workhorse that built the industry. Then came Gen 2 thin films, the innovators that showed us how to do more with less. Gen 3 gave us the peak performance champions, the absolute best of the best, but at a huge cost. And finally, we have the Gen 4 wildcards, like perovskites, that have the potential to completely rewrite the rulebook with their low cost and high potential. And that really leaves us with one last fascinating question to think about. Each of these generations has its own place, its own strengths and weaknesses, so the future of solar probably isn't about one single winner. It's likely going to be a mix of these technologies, all working together. From the silicone standard we see today to the incredible promise of flexible perovskites, one thing's for sure, the journey to power our world is far from over.